Alright, here we are on part 2. And I was setting up an idea when we have two sets that are not mutually exclusive. So they do have some common, in these events there are some common outcomes. And I'm looking at the probability of I'll say redhead, and I'm going to stick with the word or the symbol union for or, boy. Now up here for mutually exclusive events, we found that the probability of A or B was going to be the sum of the two probabilities. So let's see if that works here. First of all, since we have everyone accounted for, we can just use our counting techniques and the fact that the probability of an event is going to be the number in the event divided by all possible outcomes. The number of all possible outcomes. So that's that fraction we've been dealing with. So let's just do it by counting. We indicated that there's 17 altogether, so that's all possible outcomes. 17 different ones. And what's the probability, just by counting, which ones are red or boys? So here's red, here's boys, so the red or boys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can do it by hand, and when we can see a picture of everyone, we see pretty easily the probability of the event red or boys, red union boys, is 11/17. So let's examine how that would work and check if the probability of red or boys would work like it did up here with mutually exclusive events. So here's mutually exclusive. Down here, they are non-mutually exclusive. So we are going to test and see, is that the same? The probability of red or boys for non-mutually exclusive events, is it the same as the probability of redhead plus the probability of boys? So we know the answer should be 11/17, so we're going to test this theory. So the probability of red is 1, 2, 3, 4, 5, 6, 7 out of everyone, which is 7 out of 17. And the probability of boys is 1, 2, 3, 4, 5, 6 out of 17. So when I add those together, I get 13 out of 17. So how's that compare? It's a little higher than it should be, and perhaps you saw the mistake that took place when we tried using this rule we borrowed from mutually exclusive events. Did you notice that we counted these two in the redheads and then we counted them again as boys, which they do share those common characteristics, but they only should be counted once. So we ended up double counting them inside these fractions. So one thing we can see that we're 2 off, and notice the 2 were in that shared category. So if I take out those 2, I am at the correct one. So let's build a formula with that. So for non-mutually exclusive events, so we know they have some shared outcomes, the probability of A, and we're looking at or union B, it's going to be the probability of A plus the probability of B, but that's going to be too high because we've double counted this area in here where they're shared. And that can be told in symbol language, the probability of A and B. A intersect B. So remember, this is or and this is and. So this is the formula that will always work. Will it work for mutually exclusive events? Up here, where A and B are mutually exclusive, we cut off the formula here, but what if we kept this part? Would it still work? Well, let's talk about, pretend that these are mutually exclusive. Then we would have the probability of A or B is the probability of A plus the probability of B minus, what's the probability of both happening when they're mutually exclusive? Is no probability of that happening. So this is a 0. So this formula will turn into this one when you use mutually exclusive events, because this part will be 0. So for non-mutually exclusive events and for mutually exclusive events, for mutually exclusive events and for non-mutually exclusive events, this formula will work. So how cool is that? All right, we'll do an example or two. Let's take the playing cards. The probability of drawing a heart or a face card. Alright, so we're going to use our formula, and it said the probability of A or B equals the probability of A plus the probability of B minus their intersection. Alright, so probability of drawing a heart plus the probability of drawing a face card minus the probability of drawing a heart and a face card at the same time. So what's the probability in a deck of cards of drawing a heart? There's 1/4 hearts, 1/4 diamonds, 1/4 spades, and 1/4 puppy feet. So we have 1/4 for the hearts. What's the probability of drawing a face card? Face are Jack, King, and Queen. And there's a Jack, King, and Queen for each suit. So you have that for diamonds, hearts, spades, and puppy feet. So that's 4 suits. They each have a Jack, Queen, and King. So 3 times 4, there's 12 cards out of 52. That's reducible, but we'll mess with that in a minute. Minus, what's the probability of being both a heart and a face card? So there are a heart for jacks, Jack of Hearts would meet both of these requirements, the Queen of Hearts and the King of Hearts. So there's 3 cards that are both hearts and face cards. So if we work in 50 seconds, we get 26 50 seconds. So 13 50 seconds plus 13 50 seconds. I'm sorry, no we don't. We get 13 50 seconds plus 12 50 seconds minus 3 50 seconds. So that's 22 50 seconds. And to get a better picture of that, we might pull out a demonic decimal, which is just an approximation, but it tells us what is the probability of drawing a heart or a face card, and it's 0.4. So 0.5 means the probability of drawing it is half the time. 0.4 is a little below that. All right, see if you can do this one. What's the probability of drawing a heart or a diamond? Alright, see if you can use the formula above and the numbers that come from deck of cards land and tell me what you get with that one. Alright, you can pause it and I'll go on. So, following the formula, it's probability of a heart plus the probability of a diamond minus the probability of being a heart and a diamond at the same time. This probability of being a heart is 1/4 Probability in diamond is also 1/4. And there are no cards that are both heart and diamond at the same time. So we get 1/4 and 1/4, which is 1/2. 2/4 reduces to 1/2. So the probability of drawing a card from a standard deck that it's a heart or a diamond is 1/2. All right. That will be enough. This idea, this new formula is enough for tonight. So hopefully you will get into your probability work tomorrow, finish up your work in combinations, and be well into it. So I will be away tomorrow, but Mr. DeBloom has the answers and the know-how and the understanding to help you. All right, I will continue these videos. There'll be probably more than this one posted, so ignore the ones that are posted ahead of this. So this is Tuesday night, so there should be up one, or very soon there should be up one for Wednesday night, Thursday night. And I probably won't get Friday nights up until sometime on Saturday. All right, I will be off on vacation. Not so sure I'm going to miss you too much, but maybe a little. All right, carry on, class. Carry on.